In the last videos, we discussed the structure of a character table and the physical significance of the irreducible representations. In this video, we will understand the meaning of the Mulliken symbols used for irreducible representations. The first question is, what is the need for the Mulliken symbols? As stated in the earlier video, if we have a molecule with a symmetry, say octahedral, when we apply all the symmetry elements that belong to the octahedral point group, it will generate an identical molecular structure. So now we have a molecule, its point group, and the symmetry elements. But this does not tell us anything about how the orbitals in a molecule behave. For a chemist, it is very important to understand the orbital behavior under a particular symmetry so that they can explain the orbital interactions and energy levels qualitatively. So, we need to observe how individual bases in a molecule behave and group them based on their behavior. Here, the Mulliken symbols play an important role in naming the group of similar functions. Mulliken symbols are widely accepted so far and are used to group the irreducible representations. This is just a nomenclature, not a theory. They say how a particular function behaves under the symmetry elements of a molecular symmetry group. And it also groups the functions which transform in a similar way. Mulliken symbols are basically A1G, A2G, B1G, B2G, e.g., EU, T1G, T2G, T1U and T2U. Each letter and number has a meaning, and it is used to represent the behavior of a function under a particular symmetry element. Broadly, Mulliken symbols can be classified into three categories, such as one-dimensional symbol, two-dimensional symbol, and three-dimensional symbol. We will discuss each segment. One-dimensional representation. If there is only one function that transforms independently under all the symmetry operations of the point group and does not mix with other functions under any symmetry operations, it comes under 1D representation. The character of the identity element E is always 1 for 1D functions. For example, the 4s orbital under all the symmetry operations of the octahedral point group. One function under a particular point group may behave 1D, but the same function under a different point group may behave as 2D function. For example, dx square minus y square behaves 1D function under the D4H point group, whereas it behaves as 2D function under the octahedral point group. We will see the reason behind this in the subsequent videos. It simply means, under D4H point group dx square minus y square behaves independently and does not transform into any other function under any symmetry operation of the point group. But under octahedral point group, it transforms into dz square orbital under a particular symmetry operation. The next question is, what is the significance of A and B in 1D representation? Let's take an example of dx square minus y square and 4s orbital under D4H point group. Here, both the orbitals behave in as similar manner under most of the symmetry operations. But with C4 axis, the 4s is perfectly symmetry, hence the character is 1, but dx square minus y square is antisymmetric, that means the character is -1. So though both are 1D functions under the D4H point group, as they do not mix with any other functions, they behave differently with respect to the C4 axis, which is the principal axis in D4H. So, they cannot be placed under one group. That is why the terms A and B arise, where A represents the 1D function, which is symmetric with respect to the principal axis of rotation, whereas B represents 1D functions which are antisymmetric with respect to the principal axis. So in the representation raw, the character of A under the principal axis is 1, whereas the character of B is -1. In that molecule, all the 1D functions that transform symmetrically with respect to the principal axis grouped under A otherwise come under B. Now in 1D, there are two other symbols, such as 1 and 2. These are mainly used to create further differentiation among the functions. Whether an irreducible representation is labeled 1 or 2 is decided by a secondary symmetry element. That secondary symmetry element is fixed for a given point group, but it can be different for different point groups. For example, in C2V point group, sigma V is the secondary symmetry element. If a 1D function is symmetric with respect to the sigma V plane, then it is represented by 1, and if it is antisymmetric, then it is represented by 2. Similarly, in D4H, C4 is principal axis whereas C2 is the secondary axis. The same is true for D3H, where C3 is the principal axis and sigma H is the secondary axis, and in octahedral point group C2 is secondary axis. Finally, the symbol G and U represents the symmetry with respect to the inversion. If a function is symmetric with respect to inversion, it is represented by G, and if it is antisymmetric with respect to inversion, then it is represented as U. So, if a function is under A1G, that means it is a one-dimensional function, symmetric with respect to the principal axis, secondary symmetry element, and the inversion. A to G means one-dimensional, symmetric with respect to principal axis, antisymmetric with respect to the secondary symmetry element, and symmetric to inversion. The same can be applied for the B1G and B2G too.